you for coming. My name is Michael Monagan. I'm a professor at Simon Fraser University, which is on the other side of the continent, and it's way too early to be giving a talk.
Completely agree with you.
So the title of the talk, you can see it, Using Leslie Matrices as the Application for Teaching Eigenvalues, for teaching eigenvalues and eigenvectors in a first course in linear algebra. This is the text that we're currently using. I've taught linear algebra many times. This is the Lay text. It's actually got three authors, David Lay, Stephen Lay, Judy MacDonald. And I have an organization of the course, so I hope you can you see it at the back, Laurent? Okay. It's okay. So it's a standard course on linear algebra. I have here the chapters that we cover, the number of lectures per chapter given to each chapter. So the first chapter is linear equations in linear algebra. And in Lay's text, he has linear transformations at the end of that chapter. So it's a long chapter, so we're 9 lectures for that one. And then there's 2 relatively short chapters on matrices and determinants. A longer chapter on vector spaces, eigenvalues and eigenvectors, and the last topic in the course is orthogonality. Least squares is the application covered in that chapter, and it's part of the title. You'll notice I've got 4 lines in blue. I've always thought, what are the applications that we should teach in a linear algebra course? Because the theory is pretty standard. So one has to decide which applications you're going to teach. And you don't have a lot of time because the engineers want you to cover this topic. And the physicists insist on covering this topic. So the course is really packed. And who's taught linear algebra? Is anyone? Oh, wonderful. How many? 5? No, that's fantastic. 6? Anyone else didn't put up? 7? Okay. So 7, 8 counting myself. So by the way, it's my favorite subject to teach. I'm teaching calculus right now. I'd rather not.
Calculus is applied linear algebra.
So where was I? So you're deciding which applications you want to teach, and I've sort of settled on 4. So I've chosen as an example of a matrix multiplication, a linear system, Markov matrices, because it's nice if you have a family of matrices in the course that you're teaching. I realize that in some of the courses you don't actually cover any families of matrices, and so this is a reason to put that in. The other reason to choose that as an application is because we have the Google PageRank matrix, and the students will be interested in that. And if you can get that application in early in the course, then it hopefully stimulates some interest. For vector spaces, that's a challenge because most of the texts don't really have an application. They don't have a good one. So I've settled on using the Lagrange basis and the Newton basis representation for polynomials as the application that I want to cover. The Leslie age distribution model is the one I've chosen for eigenvalues and eigenvectors, and in this text you don't get to choose the application for orthogonality because it comes with least squares. Least squares approximation is the application. The author's already chosen that for you. It's 2 sections in the book. Even the title has it in, the title of the chapter has it there. So why am I choosing the Leslie age distribution model as the application of eigenvalues and eigenvectors? More linear algebra books have first-order linear systems of differential equations as the application of eigenvalues and eigenvectors. I have 21 linear algebra books on my shelf in my office, and I went through them, and I counted how many cover Leslie matrices, 6, and how many cover the linear systems of ordinary differential equations, and I forget, I didn't count it, but most. I think that's a poor choice to try and cover linear systems of first-order differential equations in a first linear algebra course because the students won't know what they are. Even if they've seen a differential equation in a calculus course, they won't know what a system is, and what's going to happen is that they're going to do a lot of symbol manipulation, a lot of algebra, and they won't really have a sense of what they're working with. So I don't think it's a good idea. Another reason I don't think it's a good idea, it's a lot of algebra to solve a first-order linear system of differential equations. There's a lot of algebra involved, and a lot of algebra that's got nothing to do with matrices. So I've chosen the Leslie age distribution model, which is what I want to present, as a model where the students can understand what they're working with in 10 minutes. And then it's very simple to go to the eigenvalues and eigenvectors, and it's very easy to come up with some nice applications. Third reason, in the Leslie age distribution model, the eigenvalue and the eigenvector have a natural physical interpretation. Okay, so this is the outline for the rest of the talk. By the way, who knows what the Leslie age distribution model is, the Leslie matrix? I assume maybe some? Okay, one. So what I want to do is to show you what it is. Okay, and if I can show you what it is and you're teaching the course, maybe you'd consider using this as the application. So my focus is on the linear algebra instructors, excuse me. Everyone else can stay. We're going to just show you, I'm going to show you the model. I'm going to go through so I'm going to give you a class. It's almost like a class, except it has to go faster. I'm going to show you that it is a linear transformation. We're going to take a look at the dominant eigenvalue and eigenvector. And then we're going to have some questions that we could ask students. And then in the paper that I've written, I have some resources. I have some exercises that you can use if you choose to do it. Okay, so how do I introduce the model? I'm going to introduce it with an example. I think if I show an example, the students will immediately focus. So hopefully you will immediately focus. Okay, so I'm going to consider a model for the growth of a gray seal population on Sable Island. Sable Island is an island off the coast of Nova Scotia. It's in the Atlantic. The seal, we're going to see that the seal population is growing dramatically fast, and the fishermen are not happy. They want to kill the seal population, and we're going to make a recommendation as to how they might do that. Okay. And it's going to be okay. So here we go. We are going to divide the females in a population into age groups. I'm going to label them G1 to Gn. Females only, because they reproduce. And we're going to model two things. We're going to model fertility rates, that's births, and survival probabilities, or deaths. And in the example, I have three age groups. Group 1 is seal pups, or seal babies. They are aged 0 to 4 years. And they don't reproduce. F1 means their fertility rate is 0 there, so they don't have babies. They don't have seal babies. And 6.614, 61% of them survive. And that is the problem for the fishermen, that number right there. The data was gathered over time by some biologists, I assume. Second age group, age 4 to 8 years. So the age groups are 4 years, 0 to 4 years, 0 to 8 years, and greater than 8 years. These are young adult seals. Their fertility rate is 1.26 female babies per 4 years. Okay, and survival rate about 81%. The mature adult seals, fertility rate 2. That means 1 baby per year, 1 female baby. It's in 4 years, so 2 female babies per 4 years. And survival rate about the same as this group, 81%. Everyone understand the model? That's it. right? And now I have to connect this with linear algebra. Okay, so I'm going to let little pi of t be the number of females in group I at time t. So these p for population, the population of group I at time t. And I'm going to have a population vector, p sup t, of the population of the groups at time t. Then in my example, we're going to say the population at time t plus 1 can be expressed in terms of the populations at time t as that vector. I hope you can read it. It's f1 times p1 plus f2 times p2 plus f3 times p3. So this is the number of babies at time t plus 1, right? And the number of babies just depends on the fertility rates. So in the model, the number of babies comes 0 times 0 from here, 2 times this, the population of the number of seals in this group, 2 times that, and 1.26 times this. Okay. And then the number of seals in group 2 is the number of seals in group 1 times the survival of that group. And the number of seals in group 3, the adults, is the ones that survive group 2 and the ones that survive group 3. Okay. And then we have to write it as a matrix times a vector. Now for you, that will be fairly straightforward, but I want that the students almost do this by hand to give them a bit of time to digest that I have a matrix multiplication. Because then I can tell them, oh, once you see that, then I can tell them now we can use the tools that we've learned in linear algebra to apply to this problem, because it is a problem in linear algebra. And I always like to say I will bring my big guns from my linear algebra toolkit, because we have one. In lay it's called the matrix theorem, and it's a list of, I think it goes from A to, depends where you are in the course, but it's a list of equivalences. The matrix is invertible if and only if. The determinant is non-zero if and only if. The rank is this if and only if. And it goes down, down, down. If we call that our matrix theorem, it's our big gun. We have a battleship with one big gun. Okay, and we tell them now we can fire the gun at this problem. Okay, so what do I do next? I'm going to run an experiment. Here's my matrix. I'm going to start with a population vector with 1, 1, 1. So the number of seals in each age group is the same. 100 or 1001, 1 unit. And we're going to multiply the matrix times the vector. I get the students to do the first multiplication by hand. In Maple, this is trivial. So I multiply, I do 16 steps. And these are the two values, these are the two population vectors after 15 steps and 16 steps in the first observation. So I need to give them this data calculated in advance. And what you observe is that the seal population is exploding. It's gone from 111 to over 1,000 seal. That's a huge increase in the population. And that is the problem. This is in 16 time steps, so that's 64 years. So in 64 years, this has happened. So this is a problem, right? The data is real. Okay, now, where are the eigenvalues and eigenvectors? Well, I'm going to convert these population vectors to distributions. I'm going to divide by the totals to find out what percentage of the seals are babies, young adults, and adults. Just do that. So let capital D of t be the population distribution vector at time t. It's just the population vector at time t divided by the total number of seals in the population. And then you get distributions. So we started out with 1, 1, 1. In other words, the distribution is equal. It's a third in each age group. And we run this to find the distribution vectors, and we just see what happens. And what we notice is that after 16 time steps, the distribution vector has converged. It's converged, this is at 15 time steps, this is at 16 time steps, and it's converged to about 7 decimal places, which is a lot. So it's converged to these distributions. That's 52%, almost 22%, just over 25%. And the observation is that this is an eigenvector. So what is the eigenvector? It's the distribution of the population. The physical interpretation is immediate, right? What is an eigenvector? What is it? Well, in this model, it is the distribution, it's the population distribution vector. So it has a very nice, simple interpretation. And what is the eigenvalue? Reading the slide, thus the distribution vector is converged to an eigenvector L with eigenvalue. What is the eigenvalue? Where do I get it from? Well, if I just go back a slide, if I take this, if the distribution is stabilized and I take these 3 numbers divided by those 3 numbers, then I should get the same value. So that's what I've done here. In Maple, I've just divided those 3 numbers from the previous slide, and I've got the eigenvalue, which is also converging, and it's converged to about 7 decimal places. So what is the eigenvalue? What does it mean? The matrix times this gives lambda times that, right? So the eigenvalue is the growth of the population. It's the rate of growth of the population. Very simple physical interpretation again. Okay, so what do we do with this now? At this point in the class, I have to give them a theorem because we've observed that starting at a particular population distribution, a third, it's converged. Does it always converge? Yes. If you start with a non-zero population and you have something, the matrix has some basic requirements. And so I'm going to state a theorem to tell them what happens without giving a proof, because it's beyond the scope of the course. I'll read it with you. For any non-zero initial population with the PIs positive, at least one of them positive, if at least one fertility rate is positive, then the Leslie matrix L has a unique positive eigenvalue. If V plus, lambda plus, if V plus is the corresponding eigenvector and at least 2 consecutive fertility rates are positive, and that is the case in our example, lambda plus is dominant and the population distribution will converge to an eigenvector of L. That is the limit, and I've added this, that is the limit of the distribution vector exists, and it's going to be a multiple of that eigenvector. And we have the following interpretation, physical interpretation for lambda plus. It's the growth rate of the population. So if lambda plus is less than 1, it means the population's getting smaller, it's dying. In our case, lambda plus was close to 1.5. If it's greater than 1, it means the population's growing exponentially, and if it's equal to 1, it means the population's stable. Stability is what we want, right? So this is stated without proof. And then I get the students to run an experiment where they do some calculations to see that it stabilizes. That has to be set up carefully. I just want to switch to another example. So I've used the gray seal population in my lecture. I got the data from someone in our department in statistics. It just happened. It just happened. So I got that wonderful data. And then in Lay, he has this population for the northern spotted owls. He's also divided the spotted owl population into 3 age groups. The first age group is 0 to 1 year, the second one is 1 to 2 years, and the third one means older than 2 years, and he has somehow, he doesn't say, he's got data for the fertility rates and the survival rates, and this is the Leslie matrix that you get. So I have an example here where the gray seal data has a growth rate. The dominant eigenvalue is greater than 1, it's very high, and for the spotted owl population it's less than 1. So the population is dying. So this is in North America, and there is concern about the population because it's dying. So we have one where it's greater than 1 and one where it's less than 1. Just a comment. In order to calculate the dominant eigenvalue and eigenvector for these two matrices, it's not a nice calculation, right? Because it's the characteristic polynomial, which is the method we teach students, is going to be a cubic polynomial. And it's got nasty coefficients. There's no simple factorization that you can do. It's got one real eigenvalue and two complex eigenvalues. The roots, one real root, two complex roots. So I can't get the students to solve this by hand. Obviously for Maple it's trivial, but for the students that doesn't work. So on the exams I have to concoct, and maybe we could talk about this because I have to, I have to construct, I would like to construct 3 by 3 Leslie matrices that have nice characteristic polynomials so that you can factor them easily, but they still have numbers that make sense. Okay. How are we doing? Okay. So in class that takes 35 minutes. I have 15 minutes left because it's such a simple model. You do the experiment, you show them what happens, and you do a little bit of theory, and then you can have time to do one calculation. But I have some time left. So what do? We're just going to play with the model. The idea is just to play with the model and see if we could do something. So what I've chosen to do is the following. This is in class. Here's our Leslie matrix. How would we control the population? What could we tell the government that they should do to control the population? One possible experiment is the following. Allow S1 to be a symbolic value for now. What value of S1, what must S1 be so that the dominant eigenvalue is 1? 1 means that the population is stable. It's not growing, it's not decreasing. So how would I find the value for which S1, which causes lambda plus to be 1? It's actually a very easy calculation to do. It's algebraically easy, and it's an easy for the students to do as well. We're just going to write we're just replacing lambda with 1 here. So L times x is 1 times x. You do the algebra, you get L minus I times x is 0. Means that the determinant of L minus I must be 0. You can write down the determinant, the matrix L minus I. It's just got minus 1, that minus 1, and then compute the determinant. It's going to be minus 1 times something, minus S1 times that, minus that, times that. So it's a very simple calculation for the students to do. And if you do that, I did it in Maple because I'm at this conference. I do use Maple to check things. I find as an instructor that's extreme. Actually, I'm teaching calculus, and I did the trigonometric substitution method, which is beautiful. You absolutely need Maple to check the partial fractions when you're doing that. Anyway, construct an identity matrix, compute the determinant of L minus I3. It's a linear equation. Trivial to solve. Solve it. Now look at that number. S1 is 0.103. The old value of S1 was 0.61. 61% of the seal babies are surviving. We want...
Something's wrong there, Mike.
I better not be.
From that first equation, S1 has to be negative.
No, it can't be negative. It's the survival rate. You have to subtract I.
Your determinant of L minus I3 is supposed to, that equation.
Well, you can calculate it. That's why I use Maple, to make sure I don't make a mistake. Okay, we can check it after. I've checked it many times. Okay.
Just look at the
Just
two
look at the
lines.
equation.
Look
It's
at the
got-
two
Yeah,
blue lines at the
solve the
bottom.
linear
Blue line.
equation then.
Something that,
The sum
Oh,
of two
Yeah.
positive
Right.
quantities is
oh, you know, I might have typed it in on the sheet. That's another
a
error.
minus sign in this.
There must be a minus
Minus
sign
sign,
on
right,
here.
yeah.
Okay. I wonder if I copied and pasted that wrong. This answer is right.
I believe you. I believe that.
Back to the discussion. 60% down to 10%. We have to slaughter the seal pups to control the population. That is the message. It's not just take a few out. You've got to take 80% out. But interestingly, this number tells you something about the health of the population, right? It's so healthy
They can absorb that.
because they can absorb a big hit. Yes, Rob?
I was just going to say, do you encourage contextual discussion around this? For example, I mean, these numbers, you said these were the real numbers, but of course they're derived on short-term data. And are they valid for large populations? Is the same survival rate going to hold true for large populations?
It's one population on stable island, right? It's
Yes, I know, but when it's bigger, the survival rate of the different age groups seems reasonable, would be different. I'm just wondering if you allow this kind of discussion.
no, we don't have it. The only thing we say is that the numbers could change in time. We're making assumption, and they also have error. There's some error in there. Yes.
Just in the original equation, I noticed that you don't have a time limit on the female
Correct.
reproductive ability, which really is 23, although the absolute limit is 26 years. And you're going out to 64 years, which means your numbers are going to be wrong.
That's the setup, and I'm just going to comment on that
So
in
I'm
a.
guessing you did it to simplify it?
I'm
Simplify the example.
I converted from 10 age groups to 3 because the data was the same in most of them. So I trimmed it so that the calculations were manageable for a student. Our population, I don't know whether he did that or not. The data is what it is. Let me just do another experiment. Killing seal babies is there to stir up some ire. So for an exercise, I tell the students, let's do something else. Let's shoot the seals with infertility darts. Okay, we are going to try and change the fertility rates. And since we can't tell which seals are in which age group, we'll shoot the whole lot, okay, with fertility darts. So what must this change to force the dominant eigenvalue to be 1? And they can run the same experiment and get an answer, and the answer is it's got to drop from 100% to 17%. So again, a drastic reduction for this model. Okay. In the paper, there's some technical details. One technical detail I'd like to mention is that if you look up the definition for a Leslie matrix on Wikipedia, you'll notice that the last age group always has a 0 survival rate. It's not, either they ignore it because they're not producing any babies, so it doesn't matter whether it survives or not because they can't reproduce, or it's explicitly 0. So in the model, you'll see that there's a 0 there. And the 2 examples I just presented don't follow that. So this is partial answer to your question. So there's some details in there. For anyone who's interested, the person who started working on this is Patrick Leslie, hence the name Leslie Matrices, and that's from 1945. And the original paper is in Biometrica, and I don't know much more than that other than what's on Wikipedia. In the paper, so here is an example of a Leslie matrix, which I got by trial and error, basically some experiments in Maple, but I don't have an algorithm for getting it, but I'd like one. So I want a matrix, a Leslie matrix. So the survival rates have to be between 0 and 1, and the fertility rates have to be reasonable. They're constrained, they have to be positive. And I want an example where a student can reasonably find the eigenvalues. So he's going to get a cubic characteristic polynomial, and he's going to need to factor it. And on an exam, he's going to have to do this by hand. He won't have Maple. And so in this example, there's a zero eigenvalue. So that makes factoring that polynomial feasible. You can use the quadratic formula or to find the two roots, hence the eigenvalues. There's some, so in the paper, if you get a chance to look at it, there's some theoretical exercises on eigenvalues and eigenvectors of the Leslie matrix. This matrix has a special structure, obviously, and even if you allow the f's to be symbolic, you can write down formulas for the eigenvalues and eigenvectors. There's some population control exercises in the paper, and at the back of the paper, I've gathered all the data that I found from all the different books. Some of this is from books, and some is from papers that I could get. So there's some real there's some more real data in the paper that might be useful. Okay, I think that's it. Yeah, there's a thank you for attending. Thank you. Thanks for coming.
You keep mentioning in the paper. What paper are we talking about here?
Well, I don't know. Where are the papers? I submitted a paper. It's the conference paper.
There will be a proceedings. It's being printed by Springer. That takes time, so you'll get them later.
What is it published in? Is it
The
lecture notes in computer science?
Yeah.
Oh, excellent. So if anyone would like the paper, I can email it to them. Am I allowed to do that? It's on my website, so I'm definitely allowed to do it. Yeah.
Will the slides be made available?
Yeah,
Well, I can give them to
And
you.
how?
I'll put them on my website.
yeah. We will also be putting together a website for the entire conference, which will have links to the videos of the talks and the slides when we have them.
Okay,
So.
terrific.
So who likes Leslie matrices?
Really?
Sure, Leslie does.
But there are lots of other things you can do with it as well. I mean, so, I mean, the other underlying assumption is you have unlimited resources, so that you can support
Arbitrary growth.
arbitrary growth. So that obviously.
Well, it's not built into the model.
No, it's assumed.
It's
but
assumed.
It's not that's not a
That's
constraint.
right.
So there would be other things that could come into play. And you could. It's a little bit different, but you could have harvesting. I mean, you could do.
So in my paper, I have a control with harvesting as well.
Right.
Yeah.
And I thought in Lay's book, even that proof that there's a positive eigenvalue is an exercise in there that they have. It's not that bad.
It's in the paper. So that's one of the theoretical exercises I put in the paper. I got it from Anton and Roris, not from Lay. Lay doesn't have it, but I got it from another book. Yeah. Yeah, it's a good exercise. It's doable. For a student who maybe is an honest student.
But I would, and I mean, the reason why it's a 3x3 matrix is obvious, because it is only a cubic, and it is something that can be reasonably done by hand.
Correct.
But you, of anybody, should, I would think, would be not worried about doing things by hand. I mean, once you've gotten things introduced, to do the full 10-dimensional model.
I'm in error. I think it's seven age groups for the Leslie for the gray female population. These ones are around 10 age
But-
groups.
Right, but now Maple's ideal for doing something.
Yes, yes.
And to see, for the students to see, again, that, I mean, the problems in the book are play. but the ideas that we introduce with those play problems are exactly the same things that we have. in the
I
real
think, I didn't study it, but I think compressing the Leslie matrix to 3 age groups from 7 is not changing it drastically.
Right.
It's actually still quite good.
Yeah.
And you're right, obviously the students, if they had Maple, they could do the 7 by 7 matrix straightforward, straight. But then they better type the numbers in correctly.
We've done that for that.
But the
Yeah.
constraint of the final exam is a stranglehold for what you're trying to do.
Sure, so in our department, we have 2 linear algebra courses. We have one for everyone, which doesn't use Maple or any other computer package, and we have one that does use one for our math majors, which uses a mathematical software package. Yeah. So when we say linear algebra for everyone, we mean 1,000 students, and we cannot offer tutorials and labs
Those
for that.
calculations can be done on a handheld device.
So how do you
What are the
solve a
students-
cubic? Will they be able to do that?
Yeah, of course, these
Not all of them have a
TI,
calculator.
89, whatever,
maybe.
91, whatever it is. They're little
Okay.
Every
internet stuff.
handheld calculator can do 5 by 5, 6 by 6 matrices.
What, can a student bring one of those to your exam?
To the linear algebra exam?
Yeah.
Depends which stream. For the pure math stream, no. For the everybody else stream, yes.
That's insane.
The difficulty with
We have to wrap up. I've been asked because the next talk is going to start.